All right. Hello and welcome to this talk in the LADAL Webinar Series 2022. My name is Martin Schweinberger, and together with Michael Hoare, I'm co-directing LADAL, the Language, Technology and Data Analysis Laboratory in the School of Language and Cultures at the University of Queensland in Australia. LADAL is a school-based support infrastructure for computational humanities that aims to assist anyone interested in computational or quantitative analyses of language and speech data. LADAL is also part of the Australian Text Analytics platform, ATAP, which is an open source environment that provides researchers with tools and training for analyzing, processing, and exploring text. As such, ATAP aims to provide a powerful, customizable, as well as accessible toolset for a large number of researchers who have or who do not have strong coding skills. LADAL is also part of the Language Data Commons of Australia, LDACA, which presents a national effort to make data accessible and fair. Now, before we start, I'd like to read out an acknowledgement of country, which we do here in Australia, to express our respect and gratitude towards the Indigenous people of Australia. So I'd like to say that I, as a member of the University of Queensland, acknowledge the traditional owners and their custodianship of the lands from which we are broadcasting this webinar. We pay our respect to their ancestors and their descendants who continue cultural and spiritual connection to country. I would also like to say that we recognise their valuable contributions to Australian as well as global society. Now, if you want to know more about LADAL and the resources we provide, please feel free to explore the LADAL website. No worries if you've missed any of our previous webinars. All of them are freely available on our LADAL YouTube channel. You can also find information about past and upcoming presentations in the LADAL Webinar Series 2022 on the events subpage of the LADAL website. And if you want to keep up with what's going on at LADAL, please feel free to follow us on Twitter or on Facebook. And if you have any questions, suggestions, or feedback, please do not hesitate to reach out to us via email. Now, without further ado, it's my real pleasure to introduce today's speaker, Joerg Tiedemann. Joerg is Professor of Language Technology at the Department of Digital Humanities at the University of Helsinki. He received his PhD in computational linguistics for work on bitext alignment and machine translation from Uppsala University before moving to the University of Groningen for a 5-year postdoctoral research on question answering and information extraction. His main research interests are connected with massively multilingual datasets and data-driven natural language processing. And he currently runs an ERC-funded project on representation, learning, and natural language understanding. Joerg also has a blog, and you can find the URL to his blog at the bottom of the slide. Now, hi Joerg, and thank you for being part of the webinar series. You are the closing talk, so thanks so much for being willing to contribute, and I'll hand over to you now.
Thanks a lot for the invitation, and thanks a lot for the introduction. Let me just go to the slideshow. Yes, no, thanks a lot for having me here and giving this talk mainly about this project that you were mentioning already. So there's a project that we has the title Found in Translation. It's about exploring parallel data and then trying to get some interesting information out of this, not only for computational linguistics in terms of applications, but also for learning more about languages. And that's why I added this kind of fancy subtitle, what can we learn from translations about languages and human communication? And I don't know how much I can say about this, but I will mainly talk about what kind of ideas and interests we have in this project. Let me go a little bit back to what I think is important to know about natural language processing. So I didn't really know what kind of backgrounds I would expect from the audience here. So I have some more high-level overview of what I think is important if you talk about natural language processing, and then I will also have a bit of an introduction of the tools that we are using. But let's look at natural language processing from the viewpoint of how we process signals, language signals that we can see. So if we have just language signals that we can observe, for example, text or speech, then we have some ways of applications that people are working with. For example, automated speech recognition or text-to-speech production. Or also maybe gestures and sign language can be also signals that we would like to transfer between text and those kind of sign language signals. So all of those signals are observable, which is nice. So we can do some learning on those signals to translate between them. So signal processing is some typical case where you have natural language processing going on. And as we can observe the data, we can really fully supervise this kind of task. Then, of course, computational linguistics and natural language processing is very much concerned with finding out the structure of language. And computational linguistics traditionally is very much focused on, for example, parsing the text that you're seeing and trying to see what kind of syntactic information is available, what kind of morphological structures are there, and so on. So there's some kind of structure space that we try to explore, mainly coming from the work of general linguistics, to see that certain linguistic structures we know are building up in languages, and we can try to retrieve them also by computational means. So seeing how we can produce models that can, for example, explore these syntactic structures of a sentence. And here again, as we have linguistic expertise that has been built up for many years, there can be some kind of supervision be done, provided to make this kind of procedures available, or learning procedures available for some kind of data-driven technique, for example. Now, if we then go to the way of natural language understanding, going from signals that we can observe to something that we cannot really observe. We don't really know much about how meaning should be represented, what kind of information structure we have in our head. And this kind of meaning representation is something that is really debatable. How should we present meaning, represent the semantics of some information that we are communicating to each other? So this meaning space really is an important thing that we have to define, of course, and this is kind of a hidden latent space that we need to explore. And natural language understanding certainly has to deal with the task of mapping something that we can observe, so some kind of language signals, to this hidden space to see what kind of information and meaning is behind that communication signal that we are seeing. So here we have some really different kinds of tasks that we have to look at. We cannot say that we can measure certain meaning that we see and try to supervise, for example, some learning based on those signals that we can measure and record. So what is happening in natural language processing is that typically, as we have problems in defining some kind of proper meaning representation, we use some kind of proxy tasks. So some kind of task that we need to learn certain kinds of representations that are adequate for the languages that we can see. So as you can see here, we might define certain tasks that translate or for example, read certain text and then produce other text or other signals that we can see again on the output surface. But internally, to do this kind of task, we expect that the system also needs to do some kind of abstraction on a more generic level, on a level that goes into the linguistic representations to also use the structures of languages, but then especially also going into this meaning or semantic space to provide, for example, the mapping or the connection to the underlying information that we are encoding. So the typical natural language processing task nowadays is that we try to define some kind of proxy tasks and trying to see whether, for example, a machine learning method can then abstract into some representations. So as you all have seen also nowadays, there was the deep learning tsunami, as it has been pointed out. So now deep learning is the main kind of framework that we are looking at. We try to use neural networks for using machine learning approaches to actually do this kind of abstraction. So now we have some kind of observable signals that are available from the surface, so we can really record, for example, text and speech and all kinds of gestures and all kinds of signals that we can see. But then we try to use that deep learning black box to get the abstractions for us, just by looking at the data sets and trying to abstract from those data into some representation that internally will represent, for example, linguistic structure or meaning in some sense. So one of the big questions in NLP at the moment is at least how to get a good model, so a good kind of architecture that can really pick up information from raw data. And the next question is also, how do we actually train this? So we need some kind of proxy task, as I mentioned before. So we need to have some kind of task that is a natural way of using language for certain practical things. And then from that kind of task, we would like to see what is happening in this black box and how does that black box really perform on that task, on other tasks as well. From the project that I will represent here or present in this talk, we have the idea that translation is a very good task for doing this kind of abstraction. So if you look at translation as such, then it involves quite a lot of the interesting things that we have in communication. It involves that we have to read some kind of message. So there will be a source language that we need to understand. So the natural language understanding part is naturally one of the parts of the task that we have to solve here. But on the other hand, we also have the task of generating output language. So we need to not only understand what is the message behind that input that we are seeing, but we also have to have some kind of generation component where we generate the adequate reply for that task from the source language into the target language. So as there's some nice combination here that we combine natural language understanding and generation in a naturally occurring task, we can use that proxy task to train exactly this kind of abstraction or this mapping from some signal into meaning space. And that is the main idea. So what we would like to do in the project is to see how much, if we train machine translation models, how much does a machine translation system really pick up certain structures of language, certain information about the meaning, semantics behind that kind of language signal that we are seeing, basically replicating what a translator would do, trying to understand what the translator sees, and then producing the output in a certain other language, also generating language that are fluent language and also fulfilling all the kind of grammatical and structural constraints. So if we train our machine translation models in the sense that we have something to understand and something to generate, we hope to see that representations building up inside of that model would also be interesting to study from a linguistic point of view, for example, or from a structural point of view. So in this picture, I try to kind of visualize how that might look like if you consider that there are certain languages involved. So it's just for illustration here to saying that possibly if you have very related languages, then a tool that just mechanically learns how to translate might not really go very much into very strong abstractions, as certain things are very kind of consistent. So you have languages like Swedish and Danish, where the relationship between the languages is so close that you might be able to just replace words that are very much related to each other, and the syntactic structure is very similar. So you might not need to go to a very abstract representation of some kind of meaning, because you can mechanically basically look up words that translate to each other. And the idea would be if you go to other language pairs, you might need more of an understanding what is behind that message that you're seeing in order to properly to translate it to some other language. So this is not always, it depends, of course, on what kind of things we are looking at. But in the general idea is that if you have a lot of diverse input coming in from very many different languages, then we would expect that a system that would need to take care of all the diversity needs to go more and more up in this illustration here onto the semantic or meaning space that I was putting into this picture here. So the idea in the project that we're having is that we're pushing now away from just translating between two languages, where you maybe can abstract, where we can do certain things very mechanically from some points, going into very multilingual machine translation models, where we force the system to understand many different languages, but also need to translate into many other languages in the same kind of model, in the same kind of architecture. And we expect, because we are forcing now the model to be very having this high coverage and trying to really understand all those different languages and also producing lots of different languages, we expect that this kind of model needs a different level of understanding than just a model that bilingually, for example, translates between very closely related languages. So this basically is my motivation that I want to give you here, that the idea behind this FOTRAN project is precisely this, that we are not only looking at some kind of application point of view, where we think that, okay, we want to solve machine translation, we want to help people to translate between one language and another, but we also would like to know what is actually happening inside of a translation model to see whether, for example, certain abstractions can be learned from pure data in this natural task that we can see. So also, I didn't mention that translation here is also a very nice task, actually, because we don't need any artificial setup. Translations are done naturally by people. So we can really get naturally occurring data without adding any kind of debatable annotation, for example. So we don't need annotation because this proxy task is just something that we can observe in the real world. So for that, I also find this very attractive to use translation as the main task to give this implicit supervision for general natural language understanding or processing. So let's have a quick look at the project setup. So as there's different kinds of tasks that we need to tackle, there's first of all, of course, the development of some kind of backbone where we can use the machine learning techniques that we would like to explore. So in the middle, this big sub-project one here is really about modeling and development. So we need to somehow develop a system that can really learn from raw data and try to solve the basic problem of translation to some extent. And we need an architecture that can efficiently learn. So we need to optimize the model in a way that it also can cover all those different languages. So it has to work on a multilingual setup, but it also has to efficiently learn from big and diverse data sets. So this is one of the big projects that we need to look at. We need to model and develop machine translation architectures and test them how they can learn with sufficient amounts of data. But then the more interesting parts probably come in these other sub-projects that I'm also illustrating here. So now once we have some kind of architecture and we have some kind of model that can learn from data, then we would like to know what does it actually learn? And not only, of course, the task that we're training, we want to also see what is happening internally. And this might be an interesting part also for general linguistics and people looking at communication and language studies in general, because in some sense, we would like to see how the system is picking up information from raw data, and we might have some kind of information that also we can get about general linguistic structure, or how people communicate to each other and how language is used in general. So in some sense, also making some kind of conclusions on from how our system will work to the case how human actually use languages and how languages are structured in general. So the sub-project 2 is mostly about something that is very hot, as a hot topic in our field, as we have this black box of deep learning now, and we are a bit puzzled about how it actually works. We would like to look into this black box and interpret the internal parameters and how they interact with each other. So in a sense, we can have those representations, which are basically some kind of numeric representations, very difficult to really make sense out of them. But they represent all the information that we can get from the data, some linguistic information about structure, some information about the semantics and meaning should be somewhere in there if the task of translation, for example, can be solved. So in that part of the project, we would like to interpret what we see and try to get a sense out of those different components that we have in such a model. So this is the kind of difficult part of opening the black box. And then we also have the more task-oriented evaluation packages, where we then also look at what can that model be used for. In a sense, this is the extrinsic evaluation, saying that we want to see also whether the system can, for example, do other kinds of tasks that are based on natural language understanding. So we're training now models for translation, but we would like to see, for example, also in what sense does this kind of translation model now abstract into some more language agnostic representation of semantics. So interlingua is a bit of a maybe loaded word, so maybe I should not use that too much. But we would like to see whether there's some abstraction beyond just the representations that we need to translate from one to another language, but rather, do we see actually a mapping to a more abstract semantic level that really abstracts away from language-specific things, at least across those languages that are involved in training. So in one of the task-oriented projects, sub-projects, we look at machine translation from a sense of, do we, for example, do we push the translation between languages that have very little data or no data at all? So can we, for example, see that we have an abstract level of representation that can be used to translate even between languages that it has not been trained for? So in that sense, proving that we have the effect of getting some language agnostic representation that can bridge between languages without being just the connection between two languages that we in a supervised manner learn from. So this is the machine translation part, but then we also have another part that looks at other applications. So maybe many of you have heard about transfer learning and this kind of pre-training that large language models are doing nowadays. So now that you have the fascinating world of just training some large language models, and you can apply them for many different kinds of tasks. So in a sense, this seems to show that they pick up information from the data, which is on a level that you can do some other kinds of reasoning over those representations. And here we have exactly the same idea. We would like to see how machine translation models that we train in the middle, how the representations that they pick up can be also applied to other tasks where we need to understand language. So where we need to reason over language items that we observe, some signals. So those task-oriented evaluations give us another sense of how the system can really abstract away from the purely signal point of view. So that's kind of the introduction and motivation for the project, and we are running this project, and I will give you some more details about what we are looking at in the next slides as well. But before we go to that, just also give you a bit of a background of what we need. So we need, of course, some way of getting started, and that's something that I've been working on quite a lot. So the main necessary thing that we need is of course data. So if we have a strictly data-driven approach here, so we would like to have data speaking to us and giving us the information that we need to learn from, we first have to find appropriate data sets, and we need lots of them. So I've been collecting parallel data sets, so translation data between many languages for many years. So possibly some of you know the Opus corpus. So it's probably still the biggest collection of parallel data sets which are freely available, and we are still working on extending it and improving it. So we improve especially also language coverage, which typically is one of the big challenges and problems in natural language processing, that we have a very skewed distribution over the world's languages. So even though I say that we have a large coverage, of course, we have still very little compared to what kind of linguistic diversity we have in the world. But still, Opus is nowadays already including hundreds of languages, and also especially language pairs, tries to cover them as much as possible so that we have connections between most of those languages included in the collection. I present here some extension to Opus, or extension, let's say, compilation out of the Opus data, which is a collection of different sources. So there's a lot of different inputs from different places into the entire corpus collection, which sometimes makes it difficult to really use it out of the box, as you have different subcorpora that you need to compile together. And that's why we created this Tatoeba challenge data set, which provides two different things. First of all, it provides a compilation of the training data coming out of Opus, trying to make it in a consistent way that you can basically take it with this compilation in a prepared way that nicely makes a division into training, development, and test data, for example. It has a bit more of a consistent language ID labeling, and it has also a bit of a cleanup procedure to make at least some noise disappear from the underlying collection. And the other thing is also that we try to set up some predefined test data that would be nice to use on a larger scale for more languages. And there's this this kind of community-driven website, Tatoeba, where they collect translations for many different languages. It has a lot of shortcomings, but the good thing is that they try to really push the language coverage in a sense that we have hundreds of languages already included in there. So we have a way of testing more on a global scale how things are working with many languages. But of course, you need to be aware of that this is community driven. So of course there's also some problematic cases here, but I think it's a very nice data set to get started with. We also did the basic framework of setting up the infrastructure, not only in connection with the data in Opus, but also made an infrastructure where we can systematically train machine translation models. So this Opus MT here in the middle would be the box that comes out of the data that we have collected in Opus, and we can systematically train, for example, machine translation models with given state-of-the-art architectures that are nowadays available. So with Opus MT, the basic work is done already, that we can train with all the data that we have, any kind of machine translation model, and we try to make all of those things available to anyone who would like to use them. Of course, we need to have some kind of transparency here, and that's why we really push for open data and open models in a sense that everyone who's interested in that can also get access to that. So we spend a lot of effort in making the infrastructure available for everyone and also opening up the models. And if some of you are interested in more of the details, I can give you more pointers. But for example, you can access all the models from our websites, but also through some kind of very popular libraries like the Hugging Face library that most people in NLP nowadays use for systematic studies in deep learning connected to language processing. So I don't go into the details of the other things, but if you're interested in that, you can ask me later in the question and answering session. So especially if you're interested in using translation tools, then there's a lot of interesting parts in this slide, I think. One other thing is, of course, also evaluation, and this is always tricky with automatic translation. So ultimately, we would like to evaluate manually how well the translation works. But as this is on a very large scale, systematically running for many language pairs, we also need to track with automatic metrics, how well do the systems actually perform? What is the performance of those individual machine translation models? And for that, we have now also created this so-called Opus MT leaderboard, where we can more properly track the performance of individual models and compare how things develop from different perspectives. So for example, how does a multilingual translation model compare to bilingual one? How does it compare if we change the data sets that we're training on? So with this, we have a nice kind of dashboard that can give us all the information that we need. And here's just a screenshot of things that are included in here. So you can also, for example, see the actual translations if you want to dig into the translations that you get for certain benchmarks, for example. So again, if you have more questions about this or want to explore this yourself, it's all live and available. You can click around and see what is happening, for example, for the language pairs that you're interested in. So that was the part about the kind of basic frameworks that we need. But now let's have a look at the first problem of creating architectures and models that we can use in the FOTRAN project. So what kind of models do we need? Now I just give you a very quick recap on your machine translation. As I said, I don't really know your background, so I'm not really sure what to expect, whether you know something about the typical machine translation tools that we're using. But neural machine translation is the basic de facto standard in our field for this kind of task. And it reflects somehow what I've shown before, this kind of encoder-decoder setup, where we try to reflect natural language understanding and generation in some sense, where we read a source language, try to map it into some representation, which hopefully then reflects some kind of linguistic structure and semantics and meaning. And then from that kind of representation, it then decodes, so-called decoding, it tries to produce some kind of target language out of that representation. As we have now neural networks with some kind of vector-based numerical representations, this will be the internal structure will be represented by numbers, basically. And those representations are also often called embeddings, where we try to embed the input signal into some kind of numeric representation that we can see internally in the network. So if I'm talking about embeddings, it can refer to different kinds of things. Individual words and tokens can be embedded or can be represented, or for example, a whole sentence can be represented, or even some other kind of units. Now, just to make it easier to understand what is coming afterwards, so just quick high-level overview of the typical architecture that is nowadays being used. So a neural network then is typically stacked with several layers, dividing the encoder and decoder into different components. So we have several layers of encoder steps stacked on top of each other. They read the input and map it to some kind of numeric representations in each layer, and then mixing the information in a way that optimizes the task that we are trying to optimize for example, translation. So we have encoder layers, and you have something like 6 or 12 layers or even more that try to then work on the data and trying to refine the information in certain ways, depending on the connections that the network has internally. The decoder is the same also, that we have some kind of stacked decoder that goes from some kind of input that gets from the encoder and tries to then map stepwise to that kind of information, and in the end produces some output that hopefully then becomes a proper translation in this case. So I'm not going into many details, but just give you some important things. So something that has been developed is that what is the connection between encoder and decoder? So if we have, for example, some kind of numeric representation here, as we have sequences of tokens, for example, that we are looking at, smart people have proposed that we can implement some attention mechanism. So how can we make the decoder look into different places of the encoder? And this attention mechanism is also learned, so we can learn how much a decoder needs to look into certain parts of the input sequence. Well, this is better than just giving some kind of representation and then from that global representation trying to decode the information. But instead, at the decoder point of view, the system can decide what part of the input to emphasize on to produce the next token, for example, in the output. So this kind of cross-lingual attention was very successful, but it's also interesting because it can actually be visualized where you can see what kind of connections are between input and output tokens. So a very common thing is that also people try to analyze, and we also try to analyze what is happening in that connection. Now, so maybe many of you also know about the transformers, which is now the basic toolkit that we have in natural language processing. Basically, everything is nowadays a transformer, which explores the same kind of attention mechanism, but not only cross-lingually, but also inside of the same language. So now each of the encoded layers here is made out of a sequence of hidden states, which are then interconnected. And the connections are not just sequentially going from left to right or right to left, but instead there's a so-called self-attention, which makes the system learn how to connect those hidden states that point to the tokens in the sequence that we are reading. So now all the kind of parameters need to be learned how to connect one token to another. And this kind of self-attention is then going on in each of the layers. So between each of the layers, we have self-attention trying to connect those different tokens at different positions. So a transformer basically has this structure with lots of smaller details that I'm not going into here to read through the text and try to connect the different bits. And then a decoder would also have basically a similar kind of structure, but then typically trying to decode from one side to another. So for example, from left to right, and then having the possibilities to connect to the history in various ways that need to be learned by the system. So in a sense, we have this is another visualization how you can see that a certain token looks back to other positions in the previous layer. So you can see that the weight needs to be learned, how much it should look at different kinds of positions, and those kind of weighted averages over the representations or these kind of values at those different points make the new point in the next layer. So this would be one way of just getting the new representation of a certain token. But then as we have now basic building blocks, we have those layers, we have those attention heads, that's the name of those. We can also just say that each layer should have more than just one way of looking to the previous sequence, the previously encoded sequence. So then we have multi-head attention, which means that now we just say, okay, we have 8 of those. So each layer would have 8 of those ways of looking back to the previous sequence. And we just give the model, in this sense, more capacity to learn different kinds of connection that it might use for any kind of reasoning, or not reasoning, but any kind of information abstraction that it might need to do for solving the task. So in the end, this is then giving us what is called contextual token embedding. So they are contextualized by the way that they are looking at the contextual tokens around the position that we are at that moment. So each position can look at any other position before and after. So this is of course very interesting, and it's interesting that well, from this high capacity of all the possibility of looking here and there, we would like to know where does it actually look at and why and how. So this is one of the main questions that we're interested in. So let's look at the architectures, how multilingual models can be trained. If we now have the basic model that can be trained bilingually, we can also just pipe in any kind of language into the system. So we can train not only from German to English, but let's say we train from all those languages together to all output languages as well. For making this work, we can inform the system, for example, by saying that, well, the input, it learns from looking at it. So it learns that, okay, this looks like French, so I maybe read this as a French text. But then how to know what kind of output to produce can be done by a simple trick by just adding another token, or let's say a prompt, saying that translate this into German, and then giving the sentence basically that needs to translate. And then the system, because it is trained in this way, that needs to react differently on that token, it learns how to react on that token and what to do with the text that follows after. And this is fascinating, that this is kind of enough to train and optimize a model now that also looks at this token at each point. It generates some output and knows that now I have to produce German as the target language. So this is one model, but then another, so here we would say we just take the model that I've explained before as it is out of the box. Every parameter in this model is otherwise shared. There's nothing really specific for a certain language. But we can also divide it into different kinds of architectures where we say that, okay, why not having language-specific natural language generation components, and why not having language-specific natural language understanding components, and then those connect to each other. So we can have also this modular point of view where we say that we have language-specific modules that we connect together from the encoder part to the decoder part. And then we can vary that kind of architecture in various ways, saying that, okay, we can share maybe just one part of the encoder, and saying that we have language-specific ones of reading English, Arabic, and French and Chinese, but then they come into some more common representation. They need to go through the same representation before they can be decoded into different languages. So here we have partially shared models where we can have language-specific components. And you can already see that with all those things that I've mentioned before, there's many variables and many kind of questions that we can ask. How do we share? What should we share? And what does it have for, what kind of effect does it have on the performance? And this would be one of the models that we have been looking at in our project quite a lot, which is a very component-wise model, where we say that we basically have language-specific encoders and language-specific decoders, but they have to go through some intermediate, just one layer of an intermediate representation, which then gives or summarizes the information that comes out of any of the languages that it's supposed to read from those different kinds of reading components. And then this kind of shared representation is the only thing that the decoders can look at when they have to produce the output language. And this is what we call the attention bridge. So there's, again, this kind of attention going on, attention mechanism that looks at different parts of the input, and then summarizes this into some numerical representation, which then is provided to the generation component. And now a bit more technical question is then how do we use that model then to really scale up for many languages? So just in the interest of time, I don't go too much into details of the technical problems here, but we need to then train this efficiently on some high performance computing infrastructure. So we need to have a lot of computing power to train that model, and we need to parallelize this. So if we say that we have hundreds of languages here now, we cannot just simply run this on one single machine, but we need to really divide this into a cluster where we have many GPUs available for doing heavy computing on those parameter spaces that we get here. So this is ongoing work where we try to distribute this in an efficient way between different nodes, and then train jointly the entire thing on hundreds or maybe even thousands of languages if we can get there. So this is a problem, kind of engineering problem that we're facing. Okay, so that was the modeling and architecture development part. So we are doing a lot of engineering work, as you have seen here. So we need to really develop the systems and train them. So that's a kind of interesting task from a computational point of view. But now let's have a look at representations and what they look at. So I go quite quickly through some of the things that we have found, quite interesting things that we observed. So one interesting thing that I want to just show is that so if you look at the parameters, we need to somehow find out how can we interpret certain things that develop inside of a system. So now if we look at the first model, where I said that we have a completely shared parameter space, the system just translates from any language to any other language that we have in training. And then if you remember, there was this little token in the beginning that showed the system, or told the system what kind of language to produce in the output. So this kind of flag, for example, that needs to be encoded by the internal system by some numeric value as well. So we have some kind of vector that represent this kind of token. And this representation reflects somehow the information that need to be picked up by the system for producing, for example, certain other languages. Now, the interesting thing is we can now use that representation, this kind of numeric representation, to see in what sense does it develop. So what does it really do? What does the system do when training, for example, a model that has more than 900 languages to translate between? So in this setup, we trained a system on Bible translations from and to English, and then used the same model that I explained with this language token in the beginning. And then we try to observe what is happening to the so-called embedding of that language token, and see whether we can see, for example, does it learn something about language relationships? So it doesn't know anything about typology of linguistic typology or language relationship. It just sees the text and learns to translate between all the different versions of Bible translations, for example. But if you then look at the clustering of those embeddings, it was actually quite surprising to see how well you can see clusters that reflect linguistic intuition to some extent, at least. So here, this now, you have to imagine the whole thing in 500 dimensional space, really, but you can also project that down, for example, for visualization into 2 dimensions here. And using a typical technique for this kind of projection, we can see that we can really see some clusters that reflect really language family relationships, which means that now the system really learns how to compress information about language families to make the kind of translation as efficient as possible. So things that are very closely related, they should be triggered by the same parameters. That's how you can see it. And the system learns how to optimize those kind of parameter triggering mechanism by putting the representation closer to each other. And this is quite fascinating, I would say. So it comes without any kind of linguistic input and information. Okay. Go to another thing that we looked at. So another thing that we would like to explore is that what happens with the representation of sentences, for example. So how can we see what kind of linguistic information is encoded inside of those numeric representations that we have? And here another experiment that we ran on a multi-parallel training data set. So we have Europal here as our training data. That is quite a common data set used for machine translation. It is parallel across many European languages. And we chose just a subset of some languages with a bit of linguistic variation, but also some very related languages, and try to see what happens to the encoder of English sentences when we vary, in cases when we vary the decoding part that we also training. So if we are now also trained to translate it into only one language, what happens to the understanding component of the system? What happens if we translate into 2 languages at the same time, or 3 or 4 or 5 languages? Is there any kind of effect? And here, some of the results that you can see from applying benchmark probing tasks. So there's a center val if you might know that. So there's a way of training classifiers to classify certain properties that you might want to see in representations of sentences. For example, you might want to see what is the number of the object or the subject. Does the system know about the tense of the sentence, or the depth of the syntactic tree, or the length of the sentence as one of the kind of properties that you might want to measure. So can the system really, does the system know about those properties that you can measure? And we compared here in this slide how a normal transformer, which is completely shared. So the base transformer is this shared model that I explained before. And the one to the left is the attention bridge model, where we have one bottleneck structure in the middle, and we have language dependent component as encoders and decoders. And now, having the setup where we have different numbers of target languages to train on, we would like to see whether a system that has more languages in the output would get to some higher abstraction level or not. Does it encode linguistic information in a better way if it has more languages to train on or not? So the English part is always the same, and we're only looking at the English encoder. And we can see that this attention bridge model that we had really forces the system to maybe to do more linguistic abstractions than the transformer, which has everything shared, it seems, at least from those tests. So on the x-axis, you would have a number of target languages that we trained for, and then you would have some kind of classification accuracy. The different lines refer to different sizes of the attention bridge, but the trend is more or less the same for all of those examples here, that we have an increasing accuracy if we have more languages involved in the target language as a training signal. So this is kind of a very nice example of showing that there seems to be some abstraction going on by including or improving or increasing the linguistic diversity of the training procedures. In the transformers, we might also expect this, but here you can see that it's actually not developing a lot, which seems to reflect that there seem to be different kinds of representation islands that develop inside of the shared representation space, and we can't really see a common kind of representation that needs to be affected, but instead it uses this huge capacity of the model to really reflect those different languages separately. At least that seems to be coming out of this picture. So looking also at the attention, which I said before is an interesting thing to look at. So as we have this kind of attention that tries to look at different positions in the sentence. So if we now look at this attention bridge model, so we can also see how does the system really summarize the information coming from the input sentence. And we can vary the number of attention heads, as I said before, so we can have several of those attention mechanisms looking at a sentence, and then we can see how those different heads really focus on different parts of a sentence. And what is really interesting is that the attention is very much focused on certain regions. So you can see that it's not really looking at everything and tries to blur the picture from all those different positions, but the system really tends to become very much focused on specific regions. So it seems to learn some kind of n-gram information from different parts of a sentence. And it tries to cover all those different parts, and each of the heads seems to have some kind of specialization on what to look at and what kind of information to summarize. And if you're going in this picture here, where we have a large number of attention heads, 50 of those, then we can see it first tries to cover somehow the entire sentence, the different regions, but very much focused. But then it seemed to go into more large contextual information that it tries to look at. So the highlighting means that we have a very much focus on those regions, and it seems to be then looking at more connected components of a sentence, and after that just extending that kind of information. So that's interesting as well as an outcome. to see, for example, this very focused attention. And this led to another study that we want to look at. So what really is very striking is that those models that have the capabilities of looking everywhere in a sentence, is it very common that they have this focused view on where to look at. And we saw in the transformer, for example, that self-attention really tries to look at very specific positions. So if we would have here those matrices of showing what kind of positions are connected, then it's very clear that the connection comes from the same position. That's one of the clear patterns. But also the positions just before the token will be focused on just after the tokens will be also focused on quite a lot. And then another focus will go to the end of the sentence and also to the beginning of the sentence. Is quite common. So that led to the conclusions that, well, maybe we don't even need to learn those because they seem to be very fixed, and we know that certain parts are very much important. So in that sense, it's maybe the opposite now. So we, instead of looking at what has been learned, we thought that, okay, we know that this can be learned. Maybe we can also give it as some kind of prior information. So having fixed attention patterns, meaning that we took most common attentions that we can observe by training on data and just give it as a fixed setup to a system. So that the system should look at the identical position or just before or after, or just decaying information from the context before and after. And now this is quite a busy picture, and I think I'm taking already a lot of time here. So maybe I just give you the essential, just mention the essential takeaway from this picture is that if you give those fixed attention patterns, then the system basically performs the same as, more or less the same as then it would learn it from scratch. So it seems to be not necessary that it has to learn those patterns by heart, but instead we can predefine that, okay, those kind of local connections are important, and try to encode them in a system. And this especially is interesting for resources, for languages where we have very little resources, where it would be difficult to learn all those different kinds of parameters, but instead we can predefine them, and that pushes the performance of a machine translation system by not requiring to learn this by heart. Okay, we can come back to this in the questions if you like to have any questions about this. I wonder whether I should skip this and just come more to the end to also give some more time for questions. So what I wanted to show is that we have done a lot of work in building up the infrastructure and trying to optimize the systems that we can train. And then we are looking at lots of kind of ways of interpreting the representation that's coming out. We also are looking at how to learn machine translation systems across different languages with additional information and abstraction that we can get. I wanted to say something more about the task-oriented evaluation. Can I take a few more minutes on that? Is that okay?
Sure.
Yes, sorry for being quite long. So what I wanted to just quickly show is that one way of evaluating is not only looking at the intrinsics, but we also want to see, is it possible to translate between languages that we have not training material for? So if we have the setup of the attention bridge model where we have some intermediate representation that can translate from input to some output language, we would like to see what happens if we train the system for many different language pairs, but for example, a certain language pair is not part of the training data. we would expect that if this intermediate representation is some kind of language agnostic thing, or some abstraction that goes away from just connecting two languages, we would also imagine that, for example, we can translate between French and German, even though it has never seen any examples for translating from French to German. Just because we hope that this kind of intermediate representation is on an abstract level, that also makes this possible. And this picture basically shows that this is possible. So the zero-shot translation part is the one that is interesting in this picture here. So the blue ones would be if we just translate, if we train a system on those language pairs that we have here on the x-axis. If we exclude that language pair in our training, we can see that in many cases we get almost, or we get very close to the fully supervised performance of translating between the same language pair that we are showing here on the x-axis. So this is the zero-shot example where we show that we can translate between languages even though we don't see them in training, which seems to reflect the idea that we can get some better abstraction of the semantics behind the input. So one other thing we can do is we can also apply that representation to other tasks. So instead of just doing translation, we can also apply it, for example, to tasks of paraphrasing or strings similarity measures, or natural language inference. So in case you know natural language inference as a task, the task here is to read two sentences and then deciding whether one sentence entails the other or not. So if there's a contradiction between the information given in one sentence or the other sentence, or whether the information can be entailed from the input sentence. And then this picture, sorry for all the quick numbers here, shows that if we train a system on just bilingual cases for translation, then we get some performance on those tasks. But if we train them multilingually, so we have multilingual models to train them, then we actually improve our performance of this capability of learning how to do this inference task. So this is the natural language inference. We have consistent improvement coming from bilingual to multilingual models. And for other tasks like string, some semantic similarity tasks, we can also see the same kind of tendencies, that multilingual models seem to abstract better. So again, a good example to show that this linguistic diversity improves. So yeah, I'm sorry that I took a lot of time just summing up. So what I wanted to show is that this machine translation backbone, I think, is very interesting from two different perspectives. So first of all, of course, the practical applications that we have. So we can see that we can really improve translation performance for many languages, doing some kind of transfer between languages, improving the quality of language pairs where we don't have a lot of resources for. We can also do lots of different alternatives of sharing and being more modular. So there's a lot of those kind of tasks, practical tasks that we can support, but not only translation, but also some other kinds of downstream tasks. And the second thing is that we are also interested in really exploring what are the representations really doing. So what do they represent? So analyzing what kind of linguistic structure is encoded and trying to understand the black box of deep learning in a way that reflects language structure and what we know about the semantics behind certain language strings. So in a sense, I think also the neural architectures can be interesting for general linguistics to be some kind of proxy of seeing what kind of structure is really there in language data, just being very kind of objective and just letting some system train and seeing what does it pick up and why, what kind of language relationships can be seen between different languages, for example, or between different kind of structures. So in a sense, it can be interesting to see how much the deep learning black box can be also used to explore communication structures and patterns. So there's some work going on, and maybe we need some more interaction between general linguistics and computational models to really push this forward. So with that, I think I finish up, and thanks especially some of my colleagues who did most of the work that I presented here, but also the entire team in Helsinki. And so there's more people, and we have more information on our website if you're interested. And this finally, I finish up here. So sorry for taking more time than expected.